Hello everyone, we're the 12-volt cold temperature battery testing group for ME401 Test Engineering. I'm Mark DeSantis.
I'm Eric Jang.
And I'm Jake Leggett.
Our test objective for this experiment was to determine the impact of cold temperatures on the power output of a 12-volt lead-acid battery. Some background information on the 12-volt lead-acid batteries. They're the most popular type of battery used in the automotive industry and are also used for other power supply applications. The lead-acid batteries we tested are lead-acid HEM batteries, also known as absorbed glass mat batteries. These ones are fiberglass mats that absorb the electrolyte solution between the battery plates, resulting in a higher surface area and also a higher efficiency.
So our test plan is to simulate a battery sitting outside at different temperatures for 12 hours. We started with a room temperature test of 72 degrees Fahrenheit, but then we moved on to placing the battery in a freezer at 3 different temperatures of 20 degrees Fahrenheit, 0 degrees Fahrenheit, and negative 15 Fahrenheit. And after the 12 hours, we performed a load test on the battery and measured the voltage by taking a video and recording the voltage every half second for 10 seconds of the load test. And then we turned off the load test and you can see the voltage gain back up. So we used that measured voltage to then calculate the power output of the battery. And then we compared the different power outputs across the different temperatures of each battery.
All right, for our test procedure, we first began by gathering all the necessary equipment, which we will discuss on the next slide, and then record the initial voltage reading of each battery at 72 degrees Fahrenheit. Next, set up a stopwatch next to the multimeter and begin the timer as soon as the load is applied. Record a video of the multimeter so data can be extracted. Next, hook up the multimeter to the battery and conduct a load test on each battery by pressing and holding the button on the load tester for 10 seconds at 72 degrees Fahrenheit. Then recharge both batteries up to full capacity and record the initial voltage. Then place both batteries in the freezer at the given trial's temperature, either 20, 0, or negative 15 degrees Fahrenheit, or as close as possible. Record the voltage of the batteries every 30 minutes for the next 12 hours. Then conduct another load test the same way as in steps 2 and 3 at the end of the 12-hour period, immediately after removing the batteries from the freezer. Then recharge both batteries up to full capacity and record the initial voltage. Repeat steps 5 to 8 at temperatures of 20, 0, and negative 15 degrees Fahrenheit until conclusive data is found. Lastly, analyze data to find a relationship between the power output of the batteries and the temperature. The equipment we used was a BRS Super Battery 12-volt 14 amp hour battery with a 200 cold cranking amp rating. Cold cranking amps is the amount of current in amps that a battery can deliver for 30 seconds at a temperature of 0 degrees Fahrenheit. We also used a WISE YT7B 12-volt 6.5 amp hour battery with a 120 cold cranking amp rating, which is about half the power of the BRS. We also used a Nico 100 amp battery load tester, which is pictured at the bottom. We also used a METEX digital multimeter that was given to us by the MAE lab. We used a Napa 12-volt 1 amp hour battery maintainer charger, which was used to charge the 2 batteries between our trials. We also used a thermocouple to monitor the temperature of the freezer. And the freezer we used was an Arctic King 1.1 cubic foot freezer. And for the stopwatch, we just used the regular iPhone 13 stopwatch that was provided.
The risks involved with this experiment include the potential for a leak in the battery, say in the case that the battery was dropped. To mitigate this, we made sure to handle the battery with care whenever we were transporting it. Another risk include electrical shock as well as frostbite coming from cold temperatures. To mitigate these, we made sure to both keep the battery away from water and also to wear non-conductive insulated gloves. Another final risk for this experiment is the load tester having excessive heat that could cause burns. And to mitigate this, we made sure to not touch the load tester while it was in use and to let it cool down before we handled it. The likelihood for all of these risks are relatively low.
So moving on to results here, this is the voltage versus time graph for the WISE battery, which is the smaller of the two. And if we take a look at the 4 different lines, each one represents the different temperature that it was tested at for the load test. And we can see that they all start around 13 volts. And it's really important to look at the room temperature test and see just how much higher the voltage is compared to the other 3. Which, going from 72 degrees Fahrenheit down to, 20, 0, and -15, it shows us that there is quite an impact there. And so upon the 10-second mark, we can see that the load test gets turned off, and so the voltages start to kind of gain back up. And another great takeaway from this graph is that at the -15 Fahrenheit, which is our coldest, we reached the lowest voltage, which was actually just under 4 volts. At 10 seconds. Moving on to the voltage versus time graph for the BRS battery, and we can immediately see here that the battery, since it is bigger, it holds the load much better because the voltage, kind of remains constant between that 1 second and 10-second mark of the load test. Again, they all start around 13, and we can see here that the room temperature still the highest, 20, second highest, 0, third highest. And by far our lowest is that -15, which is a great result. Moving on to the power output versus time graph for the WISE battery, which is the smaller of the two, we see that the shape is very similar to that voltage versus time graph. And that's because in order to calculate the power, we actually had to use Ohm's law, which is current equals voltage divided by resistance. And we know the voltage at every data point. As for the resistance, we used the internal resistance of the battery that we measured and then assumed that it was constant throughout all the tests and every time point. And so from that, we could get a value for the current at every single data point. And then we plugged it into the power equation, which is power equals current squared times resistance. And from that, we get these values, which we see all start around 850. And, if we look at the 72 degrees Fahrenheit one, which is, again, the room temperature at the dark blue line, we see that it's much higher than the rest, which were much colder. And if we look at the absolute minimum power output here, we see that it is the light blue line, which is our -15 degree Fahrenheit temperature, which is, it's like 80 something watts, which is very low for a battery. Moving on to the power output versus time graph for the BRS battery, which is the bigger of the two. Again, we see that it's a very similar shape to the voltage versus time graph for the same battery. That's because, again, the way we calculated the power. And, as we see here, the 72 degrees Fahrenheit, which is our room temp, is the highest, followed by the next warmest, I guess, which is the orange line, and then 0 degrees Fahrenheit, which is the green line, and our absolute minimum, which is 15 degrees Fahrenheit, which is that light blue line, which, hits a minimum of just over 1,000 watts.
For the outcomes of our experiment, the cold temperatures definitely had a massive effect on the overall performance of both batteries. The WISE 6.5 amp hour battery struggled the most in cold temperatures with a 64% decrease in power output from 72 degrees Fahrenheit to -15 degrees Fahrenheit. The BRS 14 amp hour battery also showed decreased power outputs over each temperature and had a 32% decrease in power from 72 to -15 degrees Fahrenheit. Overall, from our results, the larger the power rating of the battery, it can be seen it's more resistant to performing in cold temperatures, but both are highly impacted by the cold.
Some potential sources of error we saw were when we started the stopwatch at the exact same time as the load was applied, it usually resulted in a slight delay, which led to the voltage remaining the same for the first half second to full second, and you can go see that on the voltage versus time graphs. Also, when we would open the freezer every 30 minutes to take the voltage reading, it definitely slightly warmed the battery and the air surrounding it, and we didn't see much of an impact of the voltage as the battery was just sitting there, in the freezer for the 12 hours, not having a load applied. So we would scratch that and just leave it in the freezer for 12 hours and then give it a load test. As for next steps, we want to test a full-sized car battery to determine if it follows the same trend as these smaller batteries or to see if it's more resistant to colder temperatures. And we also want to extend our research to different types of batteries, such as lithium ion or alkaline batteries.